matters quite much how you treat it, because you see that most papers just pick one regime, like they say that we have these small particles, okay, so we do upside drag, or we have large particles, so we do Stokes drag. Here you can see that the two cases here, the upside drag and this Stokes drag are limiting cases actually. So if you have particles which have Knudsen number near 1, which means that your particles have a size which is similar to the gas mean free path, the true drag force is smaller than the two limiting cases. And this is a point which is quite easy to miss. And in most cases it will not matter much. But if you have a protoplanetary disks and you write it then on this CD as the Stokes number, the tau times the triangular frequency, you see that what you are doing is saying that you are having one particle, like which you call meter size with a stopping time 1 or so, but it's true is stopping time can be like 3 times bigger. So then the particles that actually have a Stokes number 1 here in this case is smaller by a factor 3 actually. So for my cases, for my models, it will not matter much. It means just that I will form planets with 30 centimeter size particles, not with meter size ones. But for people interested in things like fragmentation, it can be a major thing because it's much harder to break a smaller particle than a bigger one in this range. So, too bad. So then here I am showing my current models. Let's see how to go. Yeah. So then here it's a disk in a Cartesian grid. So then I captured it with a vertical field of a plasma theta like 5,000, and then you see then that it takes some time for things to start happening there, but when it does, hell breaks loose. Yeah. and hopefully it's not crashing.
So is it an m dot?
I'm sorry?
Does the m dot?
I'm showing it.
Like as a function of radius happen?
Huh? Sorry?
The m dot?
Yeah. It falls a beautiful power law actually. Something like here? Yeah. It follows a law actually with iron alpha, something like this. In the middle is something around 10 to the minus 2, in the ultrasound 10 to the minus 3, and here is around 10 to the minus 1.
And that is an
alpha formula.
Yes.
So the threshold, alpha should be constant.
Alpha could be whatever it is, but then m dot should be a constant.
M dot is dot is 3 pi sigma E, right? And E
Yes.
is alpha
Yeah.
CSH.
Uh-huh.
So you have m dot being 3 pi sigma alpha CSH. You can also substitute the sigma here by density over 2h, right? Oh, times.
Mm-hmm.
Is the opposite, so rho is 2h sigma. Oh, correct, no, sigma is 2 rho. 2h rho. So, yeah, 6h squared alpha CH. Fine. So it gives you something like this. 6h squared alpha sound speed times pi.
So it's a constant.
Yeah, it can be constant. Well, there is a rho here too. Sorry. Yeah, like it. Well, the alpha value can change. You know, like if you have rho in the sound speed, yeah,
Yeah.
canceling the alpha change.
So the dependencies of rho and r, which I don't know, they all match up such that m dot will be constant.
I didn't measure that. I didn't measure that, but yeah, I would think so.
You mentioned that m dot refers to the time at least.
Yes.
It's relatively constant in time.
In time, yeah, but I didn't check in space.
You don't have it in space.
Yes.
I mean, this is simply a measure of spurious mass sort of those things, I guess.
Mhm.
It means spurious by numerical by.
Yeah.
Mhm. So then here we show that we get the same thing everyone else gets. Like we have alpha value, which is about potentially minus 2, sorry. Yeah, no, not 2. It would be quite big. There is a largest scale of phi field there being formed too. And the kinetic energy is basically isotropic, as it should be. So now we put particles there and can see how the particles respond to the turbulence. So this is a model then with like 1 million particles. So then here I'm showing the laminar model first. So then here there is no turbulence, the particles just sediment down. So you see this very homogeneous particle layer being formed, which some people call it the pizza model. But oh, okay, like nothing really interesting happens there.
So why is there no radial structure? I mean, shouldn't there be different distinctness still?
Yeah, but I started up with a constant density profile. So then the particles follow the gas density also.
So they just fall down to 120 points.
Oh yeah, sorry.
That's what you mean, right? You wanted it to
Okay, yeah, there's no.
It just falls down to
No, it's
but if
That's
the
okay.
to stir it up, you would see this.
Yeah.
But there's nothing.
Like here, yeah, like in a real turbulent model. So yeah, like here now we have turbulence. So then instead of this homogeneous layer, then you see intense clumping happening. Now, like, and then here you also see, you know, this slight flare there.
Yeah. Yeah, you see it.
So in inner radius you have and outer radius you have buffer layers, right?
Yeah.
And they impose Heparian rotation, both on the inner and the outer edges.
Yes.
And on the outer edge, you maintain a certain mass density,
Yes.
and on the inner one also,
Yes.
such that you have 1 over r, perhaps?
Yeah, like with a pre-defined power law. Yes.
With the slope of, what is it, maybe it's 1.3?
Yeah, like it should be 1.5.
Yeah.
Yeah. Mm-hmm.
And the temperature, does it have a, what's that profile then?
Falls like R to the minus 1. Like that?
Follows from Shakur-Tsunghaev,
So that's no.
but it doesn't follow
Now
from...
you get R minus 1 R. In other constant, then I think temperature. No, sorry. The temperature should come from passive irradiation. Or is it from?
No, I think that it all comes from this thing here, actually. You know, as you want to have.
That is viscous heating. Does that get temperature going as R minus 1?
Heating only gives something if you know the cooling.
No, I think that it actually comes from the observations. You know, like you can see the spectrum, right?
I don't
Yeah, like, and it falls down. Yeah.
I see the temperature spectrum.
Yes. Yeah, because it gives you.
Yeah, that's fine. And the magnetic field?
What?
What about the magnetic field here?
I don't know. Oh, well, it's a constant vertical field. So the phase spectrum then gives you a series of like the bodies, right? Like this. So then you see that this slope here falls a law, you know, which is compatible with these black bodies here being different rings following the proportional to r to the minus 3/4. And yeah.
So is that observations then?
Yes. Yeah.
Okay.
But then this thing here, you know, is the active temperature. So if you want to pass it to a mid-plane temperature, then you do some math trick there, yeah, like, and you find out R falling like 10 of R of temperature as R to the minus 1. That's it.
Do you know why this is? Why is it?
Why is that? I knew it once at a time. I don't know it.
I know that a passively irradiated disk with no viscous heating normally quoted as a temperature going out by 1/2. I wonder if this implies some kind of thermal heating. Such a strong temperature gradient would imply that there's not just irradiation from the south, but something else staying on the road.
Okay.
So let's go on. Okay, yeah. So yeah, like we also see this, you know, that the particles get attracted where the density reaches a local maxima also, and yeah, like we see that the sedimentation by itself works up to here or so, which means that the initial density was increased by a factor 10, but well, here then this further increase was done by the pressure gradients, which we see here. You know, like we have this part here which have is slightly higher density, And here you have a huge concentration of solids there. But it's not enough yet to actually make a planet. So we have to look for some other model where we can put self-gravity. So then to add the self-gravity in my global models is not quite simple as in a local model where you can treat, like the directions as periodic. So I have been trying several different solvers for the past few months with limited success in some cases. So then I tried first, like this, phase spherical case. So you have this 3D spherical custom solver, which is used by many people, and I don't know why they do it, because it's horrible, like you have two truncations. So I tried that for the gas and for the particles, and then I saw that, I cannot trust that, the potential shows waves, which then translate to its Fourier accelerations. So if you guys can explain why people use that, yeah, please.
Is there no one-to-one mapping between spectral space and grid space anymore, as there is in Cartesian? I think you said truncation, but what do you mean by truncation?
Well, it means that you cannot solve it to infinite harmonics.
Well, you don't have infinite grid resolution either.
Yeah, true. But
okay, so
they truncate much.
Simulations.
Yeah, okay, but they truncate to a much lower harmonic actually.
So what you figure out is what is the harmonic that corresponds to your grid distribution.
Yeah, okay. And in my case, it would be quite high. I saw that, and it was harmonic about what? Well, by the grid size, right?
Yes.
Yeah,
What's, for example, the legendary L corresponding to your grid size?
Sorry? The L?
Yes. You cut it off at some maximum L value, right?
Yeah, exactly, yes, yeah.
So what is the maximum L value that corresponds to your grid size?
I don't remember the number exactly right now, but it was much larger, because if you put too many terms there,
how do you find that out?
Then much higher than the maximum one, which you put there. Because you also have here memory problems, right? And you have runtime problems there, because it takes time to calculate every single harmonic. And you also have memory problems, because you have to store, the spherical harmonics in the memory, and you have to do it for every single point, right?
So
For every single harmonic too.
Okay, so I don't know that I never worked in such. How does it mean? Is it much more costly than doing a spectral transform in Cartesian proof?
I'm sorry? Then
doing a spectral, whatever, Fourier or spherical harmonic transform.
There's no class transform in theta.
So it would only be
Theta, it's not fast.
Minor R, because there is no fast vessel.
Yeah, so the Chebyshev works quite well in our, and I don't think there's something that works quite as well as theta.
Yes.
But I don't know why the resolution is.
But the other
right. Apart from for the DFT, let's say you wouldn't use FFT, but just
Yes.
Of course, but then it would be the same order of magnitude computation problem. Yeah.
That should be same.
So, but the question, Toby's original question was whether there was one-to-one mapping. And I think the answer should still be yes.
Yeah.
It's, you can equally do a non-one-to-one mapping if you do a DFT. You may well have a non-one-to-one mapping.
What mapping are you talking about?
From spectral to Fourier and back to spectral space again.
It's an identity.
It's an identity. And if you do a DFT with arbitrarily chosen mesh points, of course you don't get that. So if you choose here the theta points arbitrarily, you also won't get that.
Your domain, what is the file extent?
2 pi.
But like, I mean, the truncation, if you try to correctly calculate the contribution from the neighboring cell, then you're close to the point where this multiple expansion does not fail to converge. So is it natural to treat the adjacent cells directly by just you calculating the 1 over x minus x prime, and then do the multiple stuff only for the stuff that's further away?
That would be like a tree method or something?
Possibly.
No, that might work. I don't try that. Probably. Let's move on. So yeah, I tried also in cylindrical coordinates. So you do it by Hankel transforms, and then yeah, I saw that it worked fine actually. So sorry, I'm okay. Yeah. Okay. So you have this here, you know, like being galaxy disk in cylindrical coordinates, and then here in Cartesian coordinates with passive Fourier transforms, and yeah, you know, like you see that they look fine. So then I tested it here, then you know, like for a massive test case. So this should break into fragments and then make its hierarchy. And this what we see here, you know, like we have this fragmentation happening.
So that's Q and C, yeah?
Yes, exactly. And you have some spirals being formed here.
So thermal or is it adiabatic?
Isothermal.
Why didn't it form planets?
Because the shock diffusion I put there had to be very, very much. Yeah.
So why did you
So
think
this is the main point.
you should get planets?
You have
Fragmentation. Exactly. Yes. Yes, really.
And Q of 1, you would form planets. But in my experience with the shear cost, the first core doesn't like to form planets.
Exactly. Not in this case, you know. But I reran this with sync particles, and it worked well actually. So then, yeah, like I coded then a sync particle module for the 10 code. Well, like it's a part of the TN body module so far, but the plan then is to move it to a particle sync file. So then basically what it does is that it checks for cells that had violated the gene's criterion, and then like there then we'll make sync particles. Then it looks for sync particles that were formed neighboring each other, and then cluster these newly formed particles with friends algorithm. So yeah, like if you see then the body file, then it has this new root in there, which which are the same particle ones. So I think I can show here actually how it works. Sorry. Well, we can live example here. So right. So here it's a run with like 50,000 particles, right? Which I put in one single cell there, right? Okay. So then, when you run it, then the particles then were removed, right? Yeah, like and then one single particle was replaced there. Oh, sorry. Now, like if you see here, then we have now this sync particle var file, SP var, where we have the mass also. So you read it with PC read SP var, object FSP or so. And if you see there what lies in there, so here, like you have the positions, these, and the masses. So, oops, hell, sorry. Oh, okay, so like here then was the first particle, which is case star. This is a Jupiter-sized planet, and then here, what the hell happened?
I think that's
Yeah, so, and then the third one here is this single particle which was formed with the 50,000 plus particles. Okay. So that was a side to illustrate. And we should move it. Okay. All right. Okay. But then there is a caveat here, which is that when you go to particles, you see that a single particle is not so smooth as you have it in Cartesian coordinates, as here. So, so it's not so physical actually to use this, because means that this particle can be trapped in one of these small wells there, right? And then so then for this reason, then we had to move back to Cartesian coordinates. So it's a step back, which we have to deal with, and then so that's what we do. I think I'll skip a couple of slides here, and then So okay, it's fine. Yeah, and then with these new models, then we can finally model how particles respond to some pressure maximum, like which we put there. So then to address the question, if overlaps will happen in this pressure maximum or not. So then we do a simple Dyson model. Means that we have this disk with alpha viscosity jump. So then here then we is like the disk keeps on being turbulent, but then here in the that zone, then the alpha value goes down, and then here like we have turbulence once again. And then what happens here is that this fuzzy jump triggers vortices, and we know the vortices trap test. So then how this thing happens, it's due to the Rossby wave instability. Well, the instability is triggered by an extremum of this quantity here, which means that it will be there when you have a pressure bounce, like local L, So the enthalpy obeys this relation here, like which means that it is executing oscillations, so it's trapped, and then the modes will grow there. It has a dispersion relation which is similar to that of Rossby waves in planetary atmospheres, and the saturated state is vortices when these waves break up. And one example here, different. What happens to different? Oops, no, I don't want that. Let it crash again. Due to your movie that it called by some reason. Yeah, right. Ripping it.
Can you switch to the console and then back to the X?
I'm sorry?
No.
What we did before was just control and delete and kill all the vertical windows.
On the backspace. To the X room, right?
What, sorry?
Did it crash?
Yeah, so.
Can you switch to Control Alt F1? And then
Control Alt F1?
Yeah. And then Control Alt F7 again.
Control Alt what?
Control Alt F7.
F. Which F?
F7.
F7. No, it doesn't change anything. Okay, this is working. Anyhow, I think that I'm already speaking for a long time, so we should move on. And
Sure, you can't just wrap it up.
no, I can't.
Maybe you can control that delete and you can just show the last couple of slides.
Yeah,
Just wrap it up.
yeah, surely.
Is that okay?
Definitely.
We'll just show the last couple of slides.
Yes, that's what I'm doing. Okay. Yeah, it's fine. Yeah. Okay, fine then. So yeah. So then the main point here is that when we have these vortices, they are quite efficient particle traps. So then when we have interacting particles there, we see that that they are so powerful that they end up making Mars-sized planets. So here I have the maximum mass, which we achieved there. So we see like planets being formed of 6 Mars mass, and then when we check for these separations, we see that it's a very bound object, because here we have Tr and mass is speed, the maximum one, and the escape is speed that a particle must have to leave the planet, and the RMS is seen to be quite low. And here I could show also the spectrum of planets which we make there. So you see here, as we go on in time, then we start making this IMF-like function, which will soon form. And then here, the red line marks the fraction, which is gravitationally bound, actually. Yeah, because we form many things which are not bound. Also. So, I don't think I have to talk about this, or following the plans. Oh yeah, one more way, like to form this thing, vortices, is by the gaps planet makes, So then the same process happens there. I mean, the gap leads to a pressure jump, which then leads to the growth of the TRWY, which then leads to vortices. And then we model it then here with many particle sizes. Well, like 4, not many, but then we see then that we form 5 super Earths here. You see this dot here has 5 Earth masses. We also form here and here, and then here too. And we see it happening also in the Lagrangian points. So then here I show how it happens when you have the planet there. So then the planet carves this gap here. The particles get attracted in the vortices, which are excited by the planet. And then here, in the 2 Lagrangian points, the particles have nowhere to go. So then, they also undergo collapse there.
What are the vortices on the outside? Is that due to the boundary? Or?
I actually think that it's a numerical thing, yes. I wouldn't trust that thing very much. But here then you see that it's a nice mechanism to form Trojan planets.
Wouldn't we trust?
Sorry?
What wouldn't we trust?
Try to show the window again. You can see on the outside, near the outer edge, these 40 vortices.
Yeah, here, right? Yeah. You will see that in later times, it will form this funny structure here due to this pressure maximum, which I think is artificial.
Yeah, and that pressure maximum goes across the break stable.
Yes.
Like now.
Yeah, soon we'll go. So you see that this thing is breaking up. So let me move on. So wrapping up. Forming Mars mass planets seems to be a simple thing when you have Rossby vortices. And a giant planet can help the second most massive planet to form. Trojan Earths, which we don't have in the solar system, can be common actually in the exoplanetary zoo. And that zone seems a promising place for forming planets. So for the immediate future, in this next few months, I will be working on extending this 2D model to a 3D with magnetic fields. Here I am saying with ambient polar diffusion, but I might try just a simple resistivity profile first to check how it goes. And that was all that I had to say. Thank you.
So, would we then, I mean, that's just then different from the coagulation picture, the transformation. It's a direct collapse.
Mm-hmm.
So, what do you think are the limits? And, I mean, why can you not go further with this model to make it work even for us, for the entire solar system?
The limit of this is that, first of all, you need particles of a certain large size. The small ones are so coupled with the gas. That even you can imagine if you took a lot of small dust grains, even if you were trying to concentrate them a lot, and it would be persistent bound, they couldn't collapse. They would sediment towards their rotating center. And that sedimentation might take so long time that any risk of turbulence would just spread it out again. Right? So I think the original gold rise and water picture of planetesimal information where this was supposed to be like millimeter sized bodies, it really doesn't work. Because they didn't consider direct forces. And that really kills that stability for the small particles. So I think the major challenge now is to how can you create enough 10 centimeter, 1 meter size bodies to get with it. And this was obviously happened by correlation somehow. And even that, it's not certain that you will build up enough meter size bodies. Maybe you only come 2 millimeters or 3 millimeters, and then they start destroying each other.
And then on the other hand, correlation alone would also not work, and you would need this mechanism like this. Is that what you're saying?
We don't talk about this in my talk. I will show that there are two different problems that we face with correlation. It's possible to cross these problems, but it's definitely not easy.
Cross, so what do you mean?
So the
combine
problem
the
is that if you have big particles, then they drift too fast inwards. So even you have these centimeter size particles, they just disappear from the disk in 100 years. The other problem is that because of the relative velocities, they usually fragment. And even if you have these big particles, they will destroy each other very fast.
Yeah, and so what's the solution against that then?
Yeah, so the solution is that you have to make the relative velocities lower somehow. And so the relative velocities are coming from turbulence and the relative drift velocities and settling and Brownian motion from the small particles. So what we can do is that we can stop the drift of the dust particles if we have a strong enough pressure bump in the disk, and they stop migrating inwards. And well, I tried to find out if this is alone enough to grow the particles further. It's not sure.
And what's the limiting speed for fragmentation? Is it 1 meter per second or more like 10?
I would say more like 10, but there are some parameters that you can tune. It just can't be the simple number. Something like meters per second.
So typically you don't want particles to collide at more than a few meters per second.
Yeah.
Then they'll destroy each other.
Yeah, but it also depends on particle size, right? I mean, like smaller particles are much harder to break.
Yes, and if you build up the same mass of particle with smaller monomers, only, then they are also more stable in solutions.
And you're saying you're doing this by turbulence, which, so the turbulence makes the mutual velocities at this small scale sufficiently small again, breaks them. Yeah. Mm-hmm. So then it works again.
But there's also the differential radio drift is also making relative speed. So the fact that a centimeter and a 10 centimeter size particle is coupled to the gas with little time scale, the centimeter size things are actually drifting through the disk much faster than the centimeter size things. These particles different sizes, even in a completely laminar disk, you get pretty high collision speed.
But that's something we can stop relatively easily. We can turn off the pressure.
So I think it's very likely that you have your global pressure gradient in the disk which is causing this. I think it's very likely you will need to make some kind of plateau there, which there are several different ways to do that. Now I will show you a few different things, but there are other ways of making these kind of plateaus. But it still seems someone who's a lot of reading on your side.
Well, I hope that we can influence with collaboration too.
Yeah, no, I'm not sure about both methods. This is to point out a lot of things.
Yes. Yeah, but isn't the time scale for cold electron much longer? It's about like thousands of years, right?
That also depends on density.
On the density.
I mean, in my disk models, which are a bit different from the minimum scale model, the gross time scale is like some 100 years.
100 years.
Yes. In the minimum
Tens
scale
of
models,
orbits. I'm sorry. So it's tens of orbits.
well, in one AU.
Okay.
100 years.
In one year, alright.
So I propose that we take a 15-minute break now. Andrew should start to do the talk, and then we can have more discussion after the talk.
Yes. It's good. Thank you.